Alright, so now we've seen an example of this model of computing, so let's try to formalize all of the pieces of this model. So we want to provide a formal definition of a Turing machine. As we've seen before, for any model of computing, we need to identify two components of it. We need to define the representation of that machine. So how is it that we actually write down like the identity of an instance of that model of computing? And then we also need to have an execution model. So how do we take that representation and actually perform some sort of computation with it? So we're going to see that this model of computing is going to be somewhat similar to what we saw for finite state automata, with just this extra stuff added in to manage the tape. So kind of like we saw with finite state automata, our Turing machine model of computing is going to have a finite set of states. So we're going to call that Q. We're also going to have some sort of alphabet for our input. So these are the characters that we might see as our input. Let's just keep calling that sigma. But because we have this tape, and this tape needs to have things like the start of tape symbol and also the blank characters on that tape, we're going to have a separate tape alphabet. So we have the list of symbols that we might see on the tape, which is going to contain at least our input alphabet as well as the blank and start of tape character, but we could have more. So in that example we saw before, we had that X character for when we had marked off something. So we're going to have this separate tape alphabet. One of the states in our set of states we can identify as our initial state, and then for this model of computing that we saw as an example so far, we have some subset of the states that we could make as final states. Now, this is not going to be consistent with every model of computing. Your book uses a different one. We're going to talk about the book's model in just a moment. But for the example we saw so far, we have final states. Other models of computing just don't have any notion of final states at all. So that final state thing may or may not be present depending on the particular version of a Turing machine that you're using. And then the complicated part of it, or one of the most complicated parts of this, is going to be that transition function, where the transition function is going to take as input a pair of values where the first thing in that pair is going to be the current state of the Turing machine. The second thing is going to be the current tape character that we saw. So whatever is the character we're reading from the tape. So the pair of state and tape character. And as output, we're going to give three things. So two things as input, a state and a character. Three things as output, which is going to be the new state, a new character to potentially write at the current location, and then a direction to move the Turing machine. And the options for that direction are going to be L for move to the left, R for move to the right, S for don't move at all, or H meaning we're done computing, halt the machine. Alright, so now that we have our representation of the Turing machine, let's look at the definition. So here I've pulled up definition 7.1 from the textbook, which gives the execution model of our Turing machine. So in this case, they called their transition function delta sub m for Turing machine m. And you can see its transition function maps a state character pair to a state character direction triple. So to start with, the first thing that happens with our transition function is we're going to initialize our tape t to be the sequence identified by the start of tape symbol, so triangle, and then all of the n characters that are our input, so x0 through xn-1, so the next n characters on the tape contain the input string. And then we also initialize these two values, I and S. So I is essentially the index of the current location in the tape. So this is which cell of the tape the Turing machine is currently looking at. And S is the current state of the machine. So which state is it currently in? And over and over and over again, so repeatedly, we're going to do the following process. We're going to apply the transition function to the current state S and the character at tape index I. And that's going to give us our triple of a new state, S prime, a character, sigma prime, and a direction D. And what we're going to do is we're going to change the state S to become S prime, our new states. We're going to change the value of S to be S prime. We're going to change the value of the tape at index I to be sigma primes, that is, overwrite that location on the tape. And then after that, we're going to update based on our direction. So if our direction D happens to be R, which is moved to the right, then change I to be I plus 1. If D is equal to L, so our direction is to the left, then we're going to change I to be the max of I minus 1 and 0. So this is basically saying if we're already at the beginning of the tape, we're just going to stay put if we have a left. So the max of I minus 1 and 0. So we can't go to a negative index in the tape. And then if the direction equals S, then we're not going to change I. We're going to keep I to have the same value. And then if D is equal to H, we're going to halt. Now from here, once we have halted, this is where the different versions of our Turing machine computing model start to diverge. So if we have, so once we halt, we have different rules for how we might actually give output from the machine. In the example that we saw with majority, the way we decided the output was based on the state we were in once we halted. So if we were in a state identified as a final state, then we return 1, otherwise we return 0. This, however, this model of a Turing machine, however, only allows us to compute functions where the output is a single bit. So we can only do decision problems or languages using this type of Turing machine. If we want to have more complicated functions where we can have multiple bits or have entire strings of outputs, then we're going to want to do something different. This different thing is what the book does. So the book does not have any notion of final states. Instead, the book states that essentially the output is all of the contents of the tape once the machine halts. So we can see here it says when the process above halts, then the output of the machine M is determined by the string that's obtained by looking at all of the symbols starting from the beginning of the tape until the first location of the tape, which contains a blank. So basically we're going to start from the start location of the tape. So start from index 0 of the tape and go up to I, where we're going to define I plus 1 to be the first blank. So every character before the first blank, that string that we get from that chunk of the tape is going to be the output of this machine. There is also this possibility that our machine is not going to halt, in which case we say that the output of the machine is bot or error or something like that.